Hello students, welcome to EPG Pathshala. I am Professor P.N. Koturu from Jammu. Today we are going to discuss about a module entitled Some Crystal Structures under paper Crystallography and Crystal Growth. So students, let us see what we are going to learn in this module. Some crystal structures, cubic crystal structures, cesium chloride structure, diamond and zinc blend structures, hexagonal crystal structures, and close-packed structures. Let us talk about some crystal structures. Different types of structures fall under 32 crystal classes depending on point group symmetry. We shall discuss some important crystal structure as we go ahead. We first take up, for example, cubic crystal structure. As has already been explained, that there are three possible cubic lattices, namely simple, cubic, the body-centered cubic, also abbreviated as BCC, and the face-centered cubic, abbreviated as Fcc lattices. Only one substance, known as alpha polonium, is reported to crystallize into the simple cubic form. Simple cubic structure has atoms only at the corners of the unit cell, as is shown in figure 5.1. In this cell, there are 8 atoms at 8 corners of the cell. Each of these atoms are shared equally by 8 unit cells, which adjoin at each corner. Thus, there are 8 corner atoms, and only 1 by 8 of each belongs to this particular cell, which makes a total of 1 atom per unit cell. In Fcc structure, the cubic unit cell contains 8 corner atoms, which are shared by 8 cells, and 6 atoms at center of the face, each of which is shared by 2 cells. Thus, in the case of Fcc unit cell, there is a total of 8 cross 1 by 8 plus 6 cross 1 by 2, that is 4 atoms in the unit cell. For BCC structure, there are 8 corner atoms, each of which is shared by 8 cells, and an atom at the center, which belongs exclusively to the cell under consideration. Thus, in case of BCC unit cell, there is a total of 8 cross 1 by 8 plus 1, that is 2 atoms in the unit cell. Almost all of the metallic elements exhibit one or other of 3 simple structures: the body-centered cubic, face-centered cubic, within brackets cubic close-packed, and hexagonal close-packed structures. The metals exhibiting Fcc or BCC will possess the full symmetry of the cubic Bravais lattice, namely the symmetry exhibited by the cubic point group M3M. The space group is obtained by prefixing the point group symbol by the symbol denoting the Bravais lattice, which is capital I for body-centered cubic and capital F for face-centered cubic. Thus, the space groups for the body-centered and face-centered cubic metallic structures turn out to be capital I, small m, 3 small m, and capital F, small m, 3m respectively. Common salt, namely sodium chloride, contains two different kinds of atoms, sodium and chlorine atoms. The NaCl structure is shown in figure 5.2. Figure 5.2a shows sodium chloride structure. Hollow circles represent sodium plus and solid circles represent Cl negative. The bonding between sodium and chlorine ions in the NaCl structure, which is a two-dimensional representation as shown in figure 5.2b, is given here. This structure has alternating Na and Cl atoms at the lattice points of a simple cubic lattice. The Na, that is the sodium atoms, are positioned on the lattice points of Fcc lattice, that is the face-centered cubic lattice. And the same is true for chlorine atoms. Thus, the sodium chloride structure is grouped under face-centered cubic Bravais lattice. The lattice points where sodium ions or the chlorine ions are located. The space group, obviously, is capital F, small m, 3 small m. The basis of the Bravais lattice consists of one sodium ion and one chlorine ion, which are separated by 1/2 of the body diagonal of a unit cube. The unit cell of sodium chloride structure may be considered as two interpenetrating Fcc, that's face-centered cubic lattices, of the two types of ions only, namely Na, that's sodium, and Cl, that's chlorine, with the corner of one located at the point 1/2, 0, 0 of the other. Each sodium ion is surrounded by 6 equidistant sodium ions as shown in figure 5.2b. As can be seen in figure 5.2a, each sodium plus ion is surrounded by 6 nearest neighbor Cl ions at a distance, say small a, and 12 next nearest neighbor Na plus ions at a distance of under root 2a. Similarly, one can find 8 Cl negative ions at a distance of under root 3a, 6 sodium plus ions at a distance of 2a, and 24 Cl ions at a distance of root 5a. Considering the structure to be a two face-centered cube sublattices, one of the sodium ions being at the origin, that is 0, 0, 0, while the other of Cl ions located at the origin, which is in the middle along a cube edge, say at point small a by 2, 0, 0. One finds 4 units of NaCl, that is sodium chloride, in each unit cube with ions located at the positions as given below. Na at 0, 0, 0, 1 half, 1 half, 0, 1 half, 0, 1 half, 0, 1 half, 1 half. Whereas chlorine ions are at 1 half, 1 half, 1 half positions, 0, 0, 1 half, 0, 1 half, 0, 1 half, 0, 0. Each ion of one type, that is Na plus or Cl negative, is surrounded by 6 ions of the opposite type as its nearest neighbors. If one ignores that there are 2 different types of ions, namely Na plus and Cl negative, the lattice may be termed as simple cubic. Cesium chloride structure. The cesium chloride structure is shown in figure 5.3. The solid circles represent Cs ions and the hollow circles represent Cl ions. The CsCl structure is basically body-centered, with Cs atoms at the body center positions and Cl atoms at the cube corners or vice versa. The Cs plus ions are on a simple cubic lattice and so are Cl negative ions. In this structure, the 2 lattices are displaced so that each ion is at the body center of a cube of atoms of the other kind. The conventional unit cell of this particular structure is so selected as to resemble a body-centered cubic cell. The edge of the cell or lattice parameter being A equal to 4.11 into 10 to the power minus 8 centimeter. Considering cesium ion, that is Cs plus, to be at the origin, that is 0, 0, 0, a chlorine ion, Cl negative, is positioned at 1 half, 1 half, 1 half. Some substances which fall under SCl type structure include CsBr, CSI, NH4Cl, CuZn, which is also known as beta brass, TiBr, and many others. Diamond and zinc blende structures. The diamond lattice is an important, less densely packed cubic structure wherein each atom is surrounded by only 4 nearest neighbors. For diamond, the structure can be considered as 2 interpenetrating face-centered cubic lattices displaced from one another along the cube diagonal by 1/4 of the length of that diagonal. The unit cell of diamond is shown in figure 5.4. One finds the unit cell to be a face-centered lattice of carbon atoms with an extra set of carbon atoms within the unit cell. Each unit cell contains 8 atoms. A projection of the atoms of a unit cell onto a 100 face is shown in figure 5.5, which is the cell plan for diamond. The displacements of atoms normal to the plane of the page is given in terms of fractions of the cube edge. The numbers 1/4, 1/2, and 3/4, besides the circles representing carbon atoms, indicate the distance below the plane for each atom in terms of fractions of the cube edge. This offers an example as of isomorphic space group, some of the reflection planes having been replaced by glide reflection planes, and the space group is capital F, small d, 3, small n. small d is replaced by m in the ordinary face-centered lattice with symbol capital F, small m, 3, small m, signifying a glide plane with a diagonal glide transition. Examples of elements which crystallize in this structure include carbon, silicon, and germanium. Compounds like zinc sulfide, symbolized as Z&S, cadmium telluride, CdTe, gallium arsenide, GaAs, InSb, and others crystallize into a structure which is similar to that of the diamond lattice, with the exception that the nearest neighbors are of opposite kind. If the two face-centered cubic sublattices are occupied by elements of different type, structure of the type of zinc blend is obtained. Figure 5.6 shows such a structure. Figure 5.6 shows the zinc blend structure. The solid circles represent Zn atoms and hollow circle represent S atoms. This structure can be represented on two interpenetrating Fcc lattices, just like diamond, except that one of the Fcc lattices contains Zn atoms while the other only S atoms. The structure of zinc blend, that is Zn-S, are possessed by many crystals, as shown in figure 5.6a. The cell plan is shown in figure 5.6b, which refers to a projection of the structure onto the base of the unit cell. The vertical height of each atom within the cell is stated as a fraction of the repeat distance in the upward direction. One can assess the closeness of packing of atoms in a given structure by determining the number of nearest neighbors that surround each atom. This number, which is called as coordination number of the crystal, may range from a maximum of 12 and referred to as close-packed structures down to only 4, as is the case with diamond and zinc blend. The latter types of structures are relatively open as compared to the former types. Hexagonal crystal structure. The face-centered cubic lattice is a close-packed one in which an atom is surrounded by 12 nearest neighbors. One can also have an alternate way of obtaining close-packed structure in which an atom would be surrounded by 12 nearest neighbors, and that is what is achieved in hexagonal close-packed structure. As said above, the face-centered cubic structure is known as close-packed structure. It is simply means that the atoms of which the element is made and assumed to be perfect spheres just in contact with one another along the diagonals of the faces in figure 5.7 are so packed that there is practically no space left between them. Such an arrangement in which the space is left empty between the atoms assumed to be perfect spheres is as little as possible in comparison to the total space occupied by the element can be done in two different ways. One is to arrange the identical spheres into a sheet of spheres so that each sphere is surrounded by 6 other spheres. Such an arrangement is schematically shown in figure 5.8, which shows close packing of atoms in Fcc crystals. Here the sphere labeled capital P is in contact with 6 other spheres which are labeled as capital Q, R, S, T, U, and V. Each of these spheres is in contact with 6 spheres. Such an arrangement creates hollow spaces as identified by solid circles and plus sign. These sheet subspheres are stacked by placing them on top of each other in such a way that the spheres in each sheet or layer get positioned into the hollow spaces in the sheet or layer below it. So the close packing may be achieved by constructing a bottom sheet or layer in which each sphere is surrounded by 6 neighboring ones, and then constructing an exactly similar layers or sheets on top of this one, using the hollow spaces between spheres in the lower layer to hold spheres which are added to the one on top of it. In a close packed arrangement, each sphere has 12 nearest neighbors, 6 of them surrounding in the same layer, 3 in the layer on top of it, and 3 in the layer just below it. In close packing, the structure is characterized by the fact that each atom has 12 nearest neighbors. One way of achieving close packed structure is by packing a lower layer or sheet, say capital A, then build a second layer or sheet, say capital B, following the procedure as described earlier. Then build the third layer or sheet wherein the atoms are added directly over the atoms in layer or sheet capital A, followed by placing the fourth layer or sheet whose atoms are positioned directly over the atoms in layer or sheet identified as capital B. Continuation of this process leads to building of an array of sheet or layers, capital A, capital B, capital A, capital B, capital A, capital B, and so on. This sequence of sheets leads to a structure which exhibits hexagonal symmetry. It is known as hexagonal close packed structure and is abbreviated as HCP. Figure 5.9 shows another way of representing close packed structures. Capital A are positions for third layer in hexagonal close packed structure, and capital C are positions for third layer in face-centered cubic structure. This representation is reproduced from Introduction to Solids by L.V. Azaroff, published by McGraw-Hill, 1960. There is one more procedure of achieving stacking of layers. That other way is to place the atoms of the third sheet or layer not directly above those of the first, but in a third set of positions, to figure 5.9, building a third layer on sheet C whose atoms are so positioned as to be directly on top of neither the ones in layer or sheet capital A nor those in sheet or layer represented by capital B. The fourth layer, that is the sheet, is then added using the positions which correspond to layer or sheet capital A, and this way an array of layers, that is the sheets sequentially termed as A, B, C, A, B, C, A, B, C, and so on, is built up. It leads to another type of close-packed structure. Fcc structure belongs to this second category of close-packed structure. Each atom in the Fcc structure has 12 nearest neighbors which are at a distance of under root 2 by 2 times the cube edge. In the case of BCC lattice, Each atom is surrounded by only 8 nearest neighbors, which are at a distance of under root 3 by 2 times the cube edge. Hexagonal close-packed lattice is shown in figure 5.10a. The face-centered cubic lattice can be obtained if the two planes, which are rotated 60 degrees with respect to one another, are inserted in between the top and bottom hexagonal faces, and the sequential order of the planes is of the type A, B, C, A, B, C, A, B, C, etc., as shown in figure 5.10b. Packing of identical spheres in hexagonal close-packed structure leads to an axial ratio C by A equal to 2 by 3 into 6 raised to 1 by 2, which comes out to be equal to 1.63. Metals which fall under hexagonal close-packed structures include Be, Mg, Zn, and Cd, amongst many others. If we have two different atoms and they are arranged on a hexagonal lattice so as to have the nearest neighbors as atoms of opposite type, the result is a structure which is known as verticide structure. ZnO and hexagonal forms of CdS, that is cadmium sulfide, and ZnS, that is zinc sulfide, are examples of this structure. So, students, let us summarize what we have learned in this module. We have learned simple cubic, the body-centered and the face-centered cubic unit cells, and how are they described. Some important crystal structures, including sodium chloride, cesium chloride, diamond, zinc blend, have been described and discussed. Hexagonal close-packed and close packing of atoms in Fcc crystals, that is the phase-centered cubic crystals, are discussed. Thank you.